12-3 starts us off talking about inscribed angles. Well, review, we've talked about inscribed triangles. What was that like? Oh, that was a triangle on the inside of a circle. So now, what if we just want an inscribed angle? Well, let's define it down here, and then we'll go back to the top of the page. An inscribed angle has a vertex on a circle. And here's the other part. And the two sides of the angle will be chords of the circle. So here we go. Here is the angle right in here. So I've got the vertex on the circle, and I have to go all the way across the circle and put the other end on another side, somewhere else on that circle. So C is the vertex, and it goes to A and B. So here's the inscribed angle. Now, when we have a circle and we make an angle, there's this magic part right here that we get to refer to and study and practice with, and this is called the intercepted arc. Notice we didn't say intersected arc, because what we're really talking about is, well, if we extended this line a little bit and this line, we only want to talk about an intersection as a point, and this thing we want to talk about all the space between this line where it crosses here and this line where it crosses here. So we're going to use the word intercepted instead. So an intercepted arc is an arc with endpoints on the sides of the inscribed angle and its other points in the interior of the angle. This last part may not be as logical or as understandable as you think, but here's what we're talking about. We have a circle, and we're going to have endpoints on the sides of an inscribed angle. So we're talking about this arc. Now, this arc has all of the other points that make it up. So there's a point on this arc that's part of the arc. And so all of these points are inside this angle. Ooh, well, what would it look like if they weren't? So here's a not inscribed, not an intercepted arc. So if we talk about here to here, what if I started caring about this arc? Whoa. Because after all, it has a vertex on a circle, and two sides of the angle are chords. So why can't this be the arc that I'm intercepting? Well, kids, because all of the points that make up this arc are not in the interior of this circle, on the interior of this angle. So this is not an example of an intercepted arc. We needed this guy here because all the points that make up this arc are inside that angle. So let's practice with these. We're going to use the inscribed angle theorem. Oh, wait a minute. You have to go back. That was just the definition. So here are the theorems. We've got the inscribed angle theorem. And all this says is that if you have this inscribed angle, ABC, then it is half of the measure of the intercepted arc. Whoa, wait a minute. We're talking about arc measurements that are in degrees, because after all, a circle is always 360, and if we have part of it, then we'll have something a little bit less than 360. So now, if we can measure this, we'll compare it to this angle, and the angle will always be half of the intercepted arc. Okay, so speed round, here we go. Let me do this. So if this arc is 100 degrees, well, maybe artistic license here, then this angle is how much? Yes, 50 degrees. And if this is a 90-degree angle, ooh, that was a bad 90. So if this is 90, how big is this arc? Yes, so if this is 90, this is, this angle is half of the intercepted arc, so that out here is 180. Now, the next theorem, the measure of the angle formed by a tangent and a chord. Okay, so tangent and a chord will always be half of the measure of the intercepted arc. Well, where's the intercepted arc? Oh, let's see here. I've got this with a tangent line, and remember, the previous lesson said tangents are perpendicular to the radius, but we don't have a radius right here. We're cutting not through the center, so I can have an angle here that's smaller than 90. So now I've got an angle that starts here, and I'm going to talk about half of the intercepted arc. So this guy right here. So whatever this angle measurement is in here, I double it to get this. Or if I know what the intercepted arc is, I can take half of it, and that gives me my angle measurement. So another way to write these is half of the measure of arc BC, which is what we're doing here, and up here is half of the measure of arc AC. We'll see this one in the exercises. So here's some corollaries, some other things that we can know about. Two inscribed angles that intercept the same arc are congruent. What does that look like? We have, I think we only need one circle for this. So I'm going to pick these 2 points and make an inscribed angle. But then I can come along and say, I get another point, and I'm going to put them with the same endpoints. So I've got this angle, and I've got this angle. But guess what? They're intercepting the same arc. And so these two angles have to be congruent. You'll see this right away with the practice, with the homework. Next one, an angle inscribed in a semicircle is a right angle. So here's a semicircle, meaning I've drawn the diameter. And now, if I'm going to use these as my endpoints and put something out here, no matter where I put this dot, as long as my endpoint is here and my other endpoint is across the circle from it, this will always be 90 degrees. And that kind of makes sense, because how many degrees are in half a circle? Yeah, 180. So that was my example up here. And the last one here, the opposite angles of a quadrilateral inscribed in a circle are supplementary. And I'll show you that right over here. Let me clear this up. So here's my quadrilateral inscribed in a circle. And now watch the magic. If I talk about this point and this point, then no matter where I am, it doesn't even have, this looks like it's half a circle, but it doesn't even have to be. So I can talk about this one and this one. This angle is intercepting some of the circle. I'll note that in black here. And then this angle, starting here and going this way, is intercepting the rest of the circle. So that means that even though I don't know the exact measurements, I know that whatever this one is and whatever this one is should add up to half of those two intercepted arcs. So this one has to, these two together will add up to 180. So if I call this A and this B, then I'm only saying A plus B equals 180. Remember, this doesn't tell you exactly what each angle will measure, only that the ones that are opposite from each other will add up to 180. Which also means, yes, that the corollary is true. If I call this C and I call this D, then C plus D together will be 180. Let's use the inscribed angle theorem now to find some of these. So, little quick review here. What are we talking about? We know that from here to here is part of a circle. From here to here is the rest of the circle. So when I look back at the angle inscribed in a circle, this angle measurement will be half of this blue arc. Half of, I'll just write it like this, half of that blue arc. And also, if I talk about this angle here, because it lands in the same spot, this angle will be half of the orange arc. And together, they make an entire circle. So if an entire circle is 360, and I've got half of a circle here, or half of an arc measurement here, and half of another arc measurement here, and they're both inscribed angles, then I'm talking about half of 360. Oops, half of 360. So I know that these two arcs together should add up to 180. Well, let's see if we can put that to work. Clean all that up. Okay, first is we need to talk about x being, x down here, will be half of the arc DEF. Why is that? Well, x is an angle and it intersects the circle here and here. So whatever x measures will be half of whatever the arc measurement is. So 80 plus 70, that's 150, and so x will be half of that. But let's fill in some blanks here. X will be half of this inscribed, half of the intercepted arc, which means that x will be half of the measure of angle DE plus EF. And arc addition works just like segment addition, no surprises there. So again, x will be half of 80 plus 70. Oops. And so half of 80 plus 70 was half of 150, which is 75. Okay, now let's take a look and see what else they wanted us to work on. Now we've got EFG, this arc here, and we can figure something out about that. This angle measurement here will be half of this arc measurement, and that's how this inscribed angle theorem works. Oops, sorry. Because EFG is the intercepted arc of D, this angle here, you need to find this arc measurement in order to find the rest of this, the entire arc measurement. And so if we know that in this circle we have 360 degrees of arc, then I can say this piece here, again, cleanup time, this piece here will be 360, take away this, take away this, take away this, right? Okay, well, there you have it. 360 minus 90 minus 80 minus 70, which is 120. So now, if I know that this arc is 120, and I care about, and y would be half of the arc that it's intercepting, so y is this angle, and I'm caring about this arc, then I've got 70 plus 120 to deal with. So that means half of, I guess actually here you could have written EF plus measure of arc FG, sorry. And so here we substitute 120. And now what's half of 70 plus 120? Well, 70 plus 120 is 190. Half of that is 95. And that's how we can work our way around a circle and thinking about the inscribed angles. Now, quick review here. What was it about the central angles? If the angle goes through, is made with the vertex on the center of the circle, then whatever this is, let's say it's x degrees, will match the arc measurement. In here, when I move this endpoint away from the center and to somewhere else on the circle, now I'm going to be half of these measurements. So there's a little summary to help you put this together and use it as we go forward. So now, here's where it gets good. It looks like we don't have much information about this circle, but wait, look at this. Do you see that there's a line going straight across that is, I would call it the diameter? Well, it's still a chord, and when a chord is the diameter, then we have a semicircle. So any angle that is formed with endpoints at the ends of the diameter will be half of the intercepted arc. Well, how much is half of a circle? Well, that's 180. And now half of that arc becomes our angle measurement in here. So now we've got angle A equal to 90. But wait, there's more. Do you see out here that we have, hold on, clean up time, there we go. Now we're saying the sum of the measures of the three angles in the triangle would be 180. So if we know that this guy is 90, then this guy over here is how much? 58. So this would be 180 minus 90 minus the 32. So that's 58. That was 180. So now, how can we find out what B is? Well, if this guy is 58 in here, and I just did that with some triangle power, then this arc from this point all the way around, I know that'll be 180, and I'm also looking at this intersection right here because I have an angle of 58 that has its vertex. Sorry, let me clear that up one more time. This is 58 and it's formed by these two lines. Well, they intersect the circle here, and they have a vertex sitting over here on the circle. So if this is 58, then the arc that I have intercepted should be twice that. So here we go, half here, twice here, and so this B measurement for the arc around the circle would be 2 times 58. 58 was the angle measurement, double the angle measurement to get the arc measurement, and so B is 116. Ah, that was fun. Let's keep going. Number 3. Measure of angle BRT. Wait a minute. BRT should be half of the measurement of this arc. So this angle BRT right in here should be half of that arc measurement. Now, the arc measurement will also be the difference of URT, take away UR. What was that? We could set it up really anyway, but I'm going to say that this RT space right here will be the difference of this larger blue arc, take away this arc, and I'm left with just this much, which is what I want. So fill this in, URT, take away the UR part, leaves me with the RT part, good. And now BRT should be half of, oh, well wait a minute, if I'm saying that this arc came from this entire thing, take away this entire thing, what do I really have? Well, I know that this arc here from T, R, and U. So from U to R to T, that's a half circle. So if the circle is 180, I'm sorry, since half the circle is the 180, that's the arc measurement here for URT. And then I'm going to look right here and see that they've labeled this arc from U to R. This angle measurement is 126. Now, hey, wait a minute. We're going back to section 2 here with a central angle. Central angles equal the arc measurements. And you're thinking, but wait a minute, Mrs. Mitchell, you just told us that these angle measurements are half. Yeah, they're half when it's an inscribed angle, not a central angle. So this is 126, the central angle is 126. If we cared about this guy out here, this guy would be 63. But we're not interested. So now, this whole thing is 180. This whole thing is 126. So how much is this part of it? A little math here. 126, and we're substituting the 180 for URT, substituting the 126 for UR, and we get this arc length from B to R to T would be 27, because this difference here was 180, take away 26 is 54. Then I did half of that and get the angle measurement. So first this arc length was 54, and then the angle in this diagram is going to be half because it is sitting on the circle. Then we're not done. Since the tangent is perpendicular, the radius of a circle at its point of tangency is a 90-degree angle. So BRS, B to R to S. We know that that is a right angle. So BRS is 90. And it's also made up of, from B to R to S, was made up of the 27 that we figured out just a minute ago. So from here, through T to R to S would be 90 minus 27. So we're saying this whole right angle is BRS, and it's made up of BRT plus TRS, which would be saying that 90 equals 27 plus this angle that we don't know. With a little subtraction, we find out that this would be 63 degrees for this angle. And let me just ask you one little corollary here. If this angle here is 63, then how big is this arc? Well, the vertex is sitting on the circle, so I have to do that doubling thing. So 126. Got it. Now, just a few problems to check if you're understanding all of this. So they say, go back to example 1 and find the measure of angle DEF. Well, I've drawn the information from example 1, and the two things that we were actually looking for in example 1 were the x value that goes right here, which happened to be 75. Because why? Because this angle intercepts an arc up here, and since the vertex is on the circumference, this arc is twice the size of the angle. So 80 plus 70 is 150. I do half of that to get the angle, and there were 75. Then the other thing they wanted to know was how big is the angle over here at D. And again, this is from example 1, so I'm just rereading what we had. That turned out to be 95 degrees. Because if we knew that this is 90, this is 80, this is 70, then over here, this had to be 120. So now we've got an angle like this, intercepting an arc from here to here. So 70 plus 120 is 190. Half of that is 95. Now, we're finally ready to find the angle which is right here, DEF. So how big is this angle? Well, look at that. We've got an angle, vertex on the circumference, which means that whatever the angle is, it'll be half of the arc that we're intercepting. Where's the arc that we're intercepting? Right here. How big is that arc? Well, it's this 90 plus this 120, so 210. And so half of that is 105. And so now we've got this guy right here, 105. Now, diagram at the right, find the measure of each numbered angle. So we're going to use this, and let me zoom in a little bit. So we've got angle 4 is probably going to be the easiest one to find first. Angle 4 is this angle, and it intercepts an arc this big. 60 plus 80, that's 140. Divide that by 2, and that's our angle that's sitting here at number 4. So measure of angle 4 is the 140 divided by 2, so 70 degrees. So now let's label what we know. Angle 4 is 70 degrees. Now, what else could we figure out here? Well, if angle 4 was 70, and I've got these other two angles over here, remember the theorem that says if a quadrilateral is inscribed in a circle, then the opposite angles will add up to, how much? 180. So 180 minus 70 should give us this angle right here. So that's 110. That kind of looks about right. And that's measure of angle 2. What else do we have? Let's see here. We've got a very interesting thing here in that from 4 to 2 is actually a diameter. So that means that this angle right here is intercepting a 180 degree arc. Oh, yes it is. So that means that angle 1 has to be half of the arc. Sorry, you can't even read that. So this arc that's being intercepted here is 180 degrees. So measure of angle 1 has to be 90. And then what else do we have? Measure of angle 3. Same logic. Watch this. Measure of angle 3. This angle has a vertex on the circumference, so whatever's in here will be half of the arc that it intercepts. How do I know how much it intercepts? Well, I know that this point here and this point here is a total of 180. And if this guy's 60, well, that doesn't even matter. As long as we know that this arc is 180, half of that will be the measure of angle 3. So measure of angle 3 is also 90. Last one. In example 3, which is just up above, describe 2 ways to find measure of angle NRS using Theorem 12-10. Well, here's what we're looking at. We've got this diagram, and we need N to R to S. And Theorem 12-10 looks like this. It's the measure of an angle formed by a tangent and a chord is half of the intercepted arc. Just like all these other angles where the vertex has been sitting on the circumference, we do half of the intercepted arc. So now we need to find this angle, and we need to use this idea of tangent plus chord. The angle will be half the intersected arc. It happens to be that the chord is the diameter. So we've got a circle like this with a diameter and a tangent line, and we want to know how big the angle is. Well, we've got 180 degree arc on the outside, and so half of 180 is 90. Or you could say that you've got 2 separate angles that we can add together, NRU and URS, but if we do angle addition, we still end up with this idea of a chord going through the center of the circle, which makes it a diameter, which means we're talking about half the circle. So 90 degrees either way. Great, now you are ready for the practice homework.